Let's pick up where we left off last time. I figured out, after testing a whole bunch of different settings in Minicom, that 7 space 1 seems to work okay with the MOS monitor and does not result in, say, oops, if I can type correctly, garbage coming up on the screen. We saw a bunch of garbage character glyphs on here, and I have since decided that, you know, well, the screen looks better. I don't really know what's going on, so let's look into it a little deeper. Big thanks to everybody supporting my channel. Thank you very, very, very much, especially the VIPs listed here. Thank you, thank you. All right, so what did I decide to do? It's like when you're a kid and, you know, you're in the back of the family station wagon on a vacation, teasing your brothers because you're bored to death after hour number 17. Don't make me come back there. In this case, don't make me pour through 2K of assembler, especially when somebody scanned a listing and half the pages are upside down. And all right, look, yes, I'm thankful. It's better than reading out raw hex and decoding it by hand. Yes, thank you. Thank you very much. But as we will see, this is ass in worse ways than a couple of bad scans. So let's look and see what's going on, kind of get the general gist of what's going on. First of all, remember, I chose 7 space 1 instead of 8 none 1, which is what the manual said to use. Now, 7's space means I want 7 data bits followed by a 0 followed by 1 stop bit. 8 none 1 means 8 data bits followed by 1 stop bit. So these two formats, 7S1, 8 none 1, both consume the same number of bits in the messages sent from the UART to the, the other end of the line, which is why I chose to use 7S instead of 7 none. Because if I chose a different number of bits, then the whole thing would be out of whack timing-wise. Why space? Well, space is the same as a binary 0. And because we send the least significant bit first up to the most significant bit on a UART line, this sends 7 bits followed by a 0 in the most significant bit. So that's 8 none 1, provided that the most significant bit is always a 0 whenever I'm sending. When I'm receiving, and this is the important part, I receive 7 bits. I then get a parity bit, which is Minicom is just going to throw that away and show me what it can, best it can. And then, you know, consume the stop bit as normal. And this will allow me to get rid of the most significant bit, which seems to have caused all the garbage on the screen. You know, it's just, me guessing my way through after, several years of suffering through people that write crappy code and don't know what they're doing. So let's have a look-see at some crappy code from people that don't know what they're doing. Now, I find it amazing, really, when a professional product has bugs like the one you're going to see in here. Maybe there's a newer version that I'm not aware of, but wow, okay? Spoiler alert, wow. All right, so let's start back here with the manual that discusses the use of the monitor here. Now, the key point here is that, we need to make sure that we don't clobber the memory that it wants to use. It talks about the highest active RAM. It scans the memory, and it's going to use the first 56 bytes that it's going to play around with what's going on. And I should reserve, 88, a bunch of bytes. Don't waste the top memory. Don't clobber it. It also says it uses the bottom memory. Okay, don't clobber that. No problem. Software entry points. This is what got me thinking. It says that, it has some subroutines in here that, we can use if we want to. And what is it? A breakpoint entry that is this. Get some I/O routines, and this is what got me thinking. There's a console input routine and a console output routine. At F009. So let's look and see how these are implemented, because most likely they're the same routines that the ROM monitor itself uses to read and write bytes to the serial port. All right, so what did it say? The console out. Now, this whole thing starts at F000, so there's a boot, a con in, a reader, and an upside down con out right here. And I want to look at con out right now, which is a jump to CO. Now, this is actually Z80 code, but it is written and assembled, let's scroll down here when it's upside up, by the CPM macro assembler, which is an 8080 assembler. So these are all 8080 opcodes and macros for the extra instructions that the Z80 can provide, like a relative jump. But in order to use the macro assembler, you gotta name your macros in ways that are compatible with the assembler. So this is a mixed bag of 8080 mnemonics and macros that expand out, as you can see, at 2004. That's a relative jump, non-zero, to this label over here. Yeah, okay, so bear with the creativity here. This is certainly palatable if you've spent any real time with Z80s and 8080s. You can jump back and forth. At least phonetically, we can follow this along. Console out does a direct jump to CO. And this is a lot like how CPM's BIOS does their thing. There's this big vector table at the beginning so that you can modify the monitor, obviously, but still use the same entry point addresses. You know these are going to be consistent over the course of time because this vector table will always be in the same place, so that's the motive, right? Or we'll assume that's the motive of why they wrote all this way. And I'm pretty confident I'm right. So here's your con out, which goes to CO. So CO is implemented down here. And it says load A with the IO byte and 3. So it's going to look at the bottom 3 bits of the IO byte. And if they are 0, it'll go to TTY out. I submit they are 0 because here's the memory that is in the machine right now. We dump D0 to say 100, so it doesn't scroll off the screen this time. IO byte is stored at address 3, 0, 1, 2, 3. It's 0. All the bits are 0, so the IO, and in fact, you can even ask it what it's set to symbolically with the Q command. It says the console goes to TTY, readers TTY, printers TTY, punch rather. P is punch. TTY, and the list device is the TTY. So they're all set to 0. And in fact, if you read through here, you'll see all the other device types are all errored out in this code anyway. So they're all set to the TTY. Fine. So TTY out. Where is that? It's down here. It's on the screen here. TTY out. What does it do? It waits until the transmit buffer is ready in the 8250 UART. Then it falls down here and says, put the C register in the accumulator, out the data port, and go on our merry way. Okay? That looks pretty good. However, who calls this routine? Now, what are we on there? If you look up here at this PERT-WAD and PERT-WA, look what it says in here. This thing prints an ASCII string into the console, onto the console. String must be terminated by bit 7 set in the last character of the string. The string will start a new line if you enter here, obviously, or it'll just print it as given if you enter at PERT-WA. This 7th bit jazz. Okay, let's see what we got here. We do what? We push B. What does it do? We must point to the string to be printed in the HL register. Wow. It doesn't even say that in the doc? Jeez. Okay, whatever. Obviously, M means the memory at the address that is in the And the memory at the address in the HL register is what M stands for in 8080 mnemonics. So it says load that into the C register, call CO, and then add one to the memory port. And we just looked at CO, so we know it's going to send the C value. It's going to write the raw 8-bit value that it carved out of memory. You see it yet? Increment H to go to the next one after you've printed it out. Then what are we going to do? We're going to load A with C, which is the old character that was printed up here, not the new one or the next one that would be printed, okay? It rotates it left, which means it takes the most significant bit and moves it over into the carry bit and says, Jemp, if there is no carry, back up here to print the byte that is the in memory at the new value in the HL register. Okay. So this prints every byte, including the last one that has the most significant bit set that is strung out in memory, which is why we're getting the most significant bit set for some random cases when we're looking at the output on the console, okay? So this is just broken as conceived because either they should have done an increment on H down here, which would affect the flags. They would have to just redo this code, or end it and shut off the most significant bit so they're not sending crap out to the console. I don't know. This is just not written very well, okay? What we could do is look up and find this CRLF. Here it is. He calls CRLF. And he got CRMSG. There we got CRLF 080. Oh, Lord. Okay, that's lovely. Then they got another message that's RSTERR plus 80 hex. So what they're doing here, this is very telling as to what's kind of going on. When it prints this message here, this is an error message for the, if you execute a restart instruction and didn't have the handler registered with your own, it goes in here somewhere and it prints this out. It says that in the manual elsewhere. So it does look that their intention is to actually have the most significant bit set on the last printed character here. Otherwise, this message would have been ERR followed by like an 80 or something, okay? This is a little less easy to understand because there's a 0 at the end of it, and if you're a C programmer, you'd say, why the heck did they null terminate it with a 0, which is how C conventions work, and then have an extra 80 over here, which may or may not have been intended to be printed. So this message down here is not the easiest one to argue about. The one up here is. So they blew it, okay? They need to get rid of that most significant bit. However, if we look at the con input routines, we will see some interesting other evidence in here. While we're in the neighborhood, though, why do you suppose it says CRLF 0 and then 80? What this is a CRLF followed by a null, followed by another null, which has the most significant bit set, and therefore signifies the end of that string. I have a teletype. I did a video on how that thing works a while back. If you look through my YouTube channel, you'll see it. And then other people do it too. It's a older teletype, and the whole print head just goes chugging across the page. And then when it gets to the right side, you say carriage return. This entire thing has to slam back over to the left, and before it starts writing the next line. So it's quite customary to waste a lot of time to give the machine an adequate period of time to settle down after a carriage return before it starts going again. So you'll send a couple of nulls down there. Now the line feed itself also consumes time. So if you go carriage return, you want to do the carriage return first so that you can waste time while it's returning, and you send as many other bytes that are all non-printing and not going to harm the printer in any weird way. And a null is a character that has no width and no glyph. So on a teletype, it's just literally it's there to waste time. And the thing will just sit there going chug, 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 and then not move at all. It'll just sit there waiting for data. And it kind of looks like it's getting ready to breathe to start going at the beginning of a race or something, you know. Anyway, so that's why this is the way it is. They want to say carriage return, and then they're wasting 3 character times worth of data here. So you do want to send this null out to the printer, preferably without the bit set over there. Okay, so let's now move over to their console input routine, because there's something more telling over there. Con in ultimately calls con I. What do we got to do? We got to go back up to the beginning. All right, now let's look at the con in here at F003, which calls CI. If we scroll down here to CI, we'll see, is it set to 0? We know it is, so it calls TTYIN, which is down here. And it says check the status until it's ready. When it's ready, read the data and return. Okay? You'd think that's okay. Provided that it's okay to read in an 8-bit value that never came from your own code, because it might have the most significant bit set up there, which would be annoying and cause potential problems. Now, if you scroll around in here, there's also another routine somewhere, I saw it while I was playing around, called con I. Where is it? It's up here someplace. There it is. Which calls the CI we were just looking at. Then it throws away the parity bit, it says, which is not the parity bit, the most significant bit here, and then returns. Okay? Now, it may be the parity bit if you're sending a 7-bit data followed by some sort of parity bit, but this is why we need to make sure we send enough bits to this thing here, because it expects there to actually be 8 bits. Sometimes it uses con I, other times it uses the CI, and it might have junk in the most significant bit down there. But this is a CPM-ish thing. For some of the routines, when you look at the BIOS documentation, it says strip off the most significant bit, and they refer to it as a parity bit in their doc as well. So, in the defense of whoever wrote this, whose sole purpose in life is to waste hours of my time last night, there was a theme to this whole thing, right? So, okay, that explains the noise, that explains why 7 none 1 will shut this thing up, and we can kind of get by with all this and not expect there to be any real problems, because when we're doing 7S1, even if they use the routine that does not strip the so-called parity, it will be 0 because space is the 0 in that bit position. Are we good? Now let's look at something else in here. They have a routine, I guess we should look at the doc first before I use it, called read, which is one of these commands here, right here. Page 313, which is I don't know where, so we just have to scroll until we find it. Is that section 313 or page? I don't know. I love it. 310, 37. Just shoot me. Oh my gosh. Oh my God. Maybe it is the page. Okay, there we go. Monitor. Okay, read. There we go. 372. I think in there, I think it might have said 372 on the left and 313 on the right. In any event, okay, so this thing here, and make sure we read it all this time, John. It allows you to read an Intel hex format. Because, you know, if you have a paper tape, you have all this stuff on there. One popular thing you could put on a paper tape and read it in your terminal is an Intel hex file, which is an ASCII printout of a bunch of hex characters and some CRCs and stuff like that for storing binary images in printable characters. So the R command will let you do it, and you can put a bias value on there. So it says, look, even though the paper tape says to load this at address 100, go ahead and read it, but put it at 100 plus some bias, like 2000. Then I can make it go in at 2100, so I don't clobber something that it might otherwise be addressed to do. So what does it say? It checks for errors while reading the paper tape. Okay. If it counters one, the program will be aborted. There is no error that I'm aware of that is ever being reported when the paper tape is aimed at the console/TTY input, so that won't happen. And then it says it also provides error checking for the program loaded into memory. If an error is found, the address of the byte in error is displayed, along with an 8-bit representation of a bit error, where a 1 indicates the bit in error. For example, if it says this, that would suggest that bit 4, which is a horrible example to have chosen, of the byte in memory location F038 is in error. Okay, that's great. Bit 4. Does that mean 1, 2, 3, 4? Or does that mean 0, 1, 2, 3, 4? In this case, it doesn't matter. But it gives you no help whatsoever as to what number that bit is. I did this in one of my own examples recently, and somebody pointed it out and said, it'd be more obvious, more useful to use any other example, would suck much less. And I couldn't believe I did that. I am so sensitive to this sort of thing. As a reader, I guess, more so than as a writer. So I see how this happens. Guilty, but come on. Surely they have an editor. No, they don't have an editor. Clearly they don't have an editor for this documentation. Be careful. I believe 0 is over here, okay? Okay, so after it's been read, controls return to the monitor. If the entry address in the EOF record is 0, okay, it'll go back to the monitor. If it's not, then control will go to that address and the code will begin running. So the important safety tip, if we're going to use this, and we are, make sure that you either put the right address in the EOF record or a 0, so that machine doesn't take off in some haphazard manner. Now, this is an interesting thing. If the current physical device is assigned to the reader logical category, if the current device is the teletype, yes, the monitor will respond to the read command by reading a program in binary typed by hand from the console, unless you provide paper tape reader routines for the What? First of all, I'm real sure I don't type in binary. If you look at the code in there, which I did, it's going to call the regular reader routine. What they mean is you can type in an Intel hex file in ASCII on the typewriter, teletype on the console, if you want to. And because you just saw all these routines from the Intel I/O byte are set to the teletype input, the UART. Anyway, this is the only way we can use it. So, okie dokie. All right. So now what do we do? All right. Now, unfortunately for me, I chose to use the world's worst Z80 assembler when I started doing some projects a while ago, and I don't yet have a nice cross assembler and set of tools set up, so I'm still going to use the same crummy one that I've been using. Let's look at this program right here. Now, this is super duper copyrighted. You better not steal it. As a joke, I put this in here. 0 the accumulator, count, store it, and go in a loop, okay? So that's this super secret sauce here. If you compile this, the use of this very simplistic assembler, which, you can get a lot of mileage out of this. I did the entire CPM BIOS and all bunch of apps and stuff. I've been using this for years. I used it on purpose because if you're just getting started and dabbling with machines of that retro era, I remember the annoying problems I had dealing with assemblers that generated these Intel hex files and running linkers and all this other crap you have to go through, which is normal, by the way. We still do that to this day, and that's the right way to do it. But I was annoyed by, if you want to write just a simple, dumb program like this, I don't want to take 9 hours. Get to the point, assemble it, done. So this assembler goes directly to binary. And the way this is configured, I say write it to standard out. And oh, by the way, provided a listing while you go, so we can see the source code with all the object code and the addresses over on the left. That's great. So I take the output and I pipe it into this srec-cat function, read from standard in, which is the output of the assembler, and create a hex file like I would have in the first place if I used an older, more sophisticated, fancier assembler whose output was an Intel hex file. So this is a way to convert it into one and say, mark the addresses in the hex file starting at 1000. That number there has to match the origin in here or it won't work, and write it into this hex file here and use Intel format with a 2-byte address and only put 16 bytes per line. With these settings, you will see that it matches, if you're used to seeing these in days of yon, the kind of these are the line lengths that we used to have in the old days. I did this on purpose because I assumed correctly, we'll look at the code in a minute, that the read function in the MOS monitor may not be able to tolerate anything other than these oldie-timey style formats that were in use at the time, and that is a 16-bit address followed by a line that's not terribly long, okay? So this is the size of the lines that we used in the old days. Here's my end record, by the way, and the way this works is there's a record type and an address in here, and then there's a checksum over here. Each one of these is like a CRC. The last byte is a CRC of the preceding data, so it can determine if there's an error in transmission. And when I first read this over here, I took this as to mean that if it found an error, that would be the kind of errors it was checking. And no, that's not what you're going to find out. So let's look and see what happens if I type that in at the terminal. All right, so here's the R command. Now I'm running at 3800 baud, and I'm at full speed. There's no delays or anything configured. So this thing is going to crap all over itself. All right, now what did it just print, okay? And why is it hung? All right, remember it says if there's an error, it'll say here's an address and there's an error. What does the error mean? I don't really know. It says that it'll do something. The idea is we look at the code. What it's doing is it's asking if I write it into memory and I read the memory back. That's what they're talking about here. And the memory doesn't have the value I wrote into it, then it'll say it's wrong. So according to this, every bit is wrong. And wow, I don't know what it's doing here. Sat there forever getting more data. And it kind of died ultimately out of there. So what the heck's going with that? Well, first of all, let's see what it really accomplished here, right? Let's cat the list file for this hex file. What did I do? I go into address 1000. I got XOR A and some other AF321810, all right? Let's have a look, see it. What's address 1000? AF3C, blah, 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 blah. Okay. AF, not feeling the love here. There's a 3C down there, but okay, it got the first byte, and then it crapped out. You'll notice it says the first byte's wrong, the next byte, every byte is wrong, okay? Every bit of every byte is wrong. Let's go into the setup here, terminal settings, and add a delay, F. 20 milliseconds. I'm going to just guess. And a new line delay. I don't know if I need a new line delay. Let's just do that and see what happens this time. There's a fill command, 1000 to 1100. Let's put a F5 in there. All right, so it is a known set of data. Let's go back here again. Cat prog1.hex. Take 2 with a delay. The reason we need a delay, oops, helps if you do the R command first. Now we'll notice that we go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Every bit of every byte is wrong, according to this. All right, and if we count all this out, there's 16 bytes worth of data there. Then we'll send the next record of data out. Every byte in that line is completely wrong. And then let's send the end of file marker thing down there that has the zeros in there, so it should come back to the prompt if it read it. It did come back to the prompt and crapped all over itself. So according to this, everything is as wrong as it possibly could be, except for the fact that it was entered in perfectly all the way through. Let's have a look-see and compare this. There's the listing right there. AF32 1810, AF32 1810, 3C32 1910, 3C32 1910 right there, 3C32 1A10, 3C31 A10. Now a bunch of zeros because I put a bunch of no-ops in there for a reason you'll see in a minute. And then we go for a while and it says C30010 right there, a couple of 5As right there, which is the data in there, and it says end up program. It worked perfectly. Yet, according to this, the whole thing is wrong. And what's going on down here? All right. It took me a while to figure this out. Let's first run this. Make sure that, things are what we expect. Clearly, it all got in there. We just hand-checked every byte. It's fine. Now, there's a command, and we can say go, and you can say run, start at 1,000, and I usually put like a bag of no-ops in there in a place, so it makes it easy for me to type in an address like this for the breakpoint. So if I can say start at 1,000, and here, it'll execute this stuff and stop. And what does this do? XOR A, it makes A 0, right? Anything XORed with itself is 0. Remember that. Then I say put A into the memory at address where S1 is. That's these guys down here. Add 1 to A, store, add, store, da 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 da. So this should put a 0, 1, and 2 in here on top of these 5 A's. If we run it, by saying go, 1010. It came back, which is always a good sign, because when you do this, your programs oftentimes will die before you debug them, and the whole thing goes nuts. You don't know what you're at, and the whole thing is seized. I typed it in wrong. D1000, 1100. What do we got? There's my 012, which replaces the 5A, 5A, 5A. So not only did it upload fine, it ran, did exactly what it should have done, and yet everything is wrong. So the fact that everything is wrong is very dubious. It's consistent, I'll give it that much. So, back to the documentation here. Okay, so this write-up is clearly what they meant it to do. But if we go down to page 87, make me come back there, and we look through here, we see a read function. Read an Intel hex format paper tape from the current paper tape reader. If non-zero address is specified in the end, we will go there. Otherwise, we'll go back to the console. All right. What does it do? Get the offset bias. So this is parsing the command line argument. I'm not going to look at that. Red 0. Bias into there, save it, do stuff. Okay, it's reading bytes. Look for the start of a record. So what it's looking for is the colon. If not, it ignores everything it gets. So you can send it an arbitrary amount of crap followed by a colon because it doesn't check anything. Okay, shows me a lot. So much for error checking. Initialize the checksum, get the record length. So what happens here, here's our program, is the first thing it wants to do is get, what do we got here? How do I get all this on here? It's margins, people, margins. Here we go. I can actually read it now. All right, so what is it doing here? Get the record length is the first byte after this thing, right? So I got a 1, 0, it'll be a 2-byte value. What do we got? Get the record length, call byte. It must read 2 digits and convert them to binary or something like that. If it's not 0, or no, if it is 0, if it got a byte that is 0, we can look at the byte routine. If you want, I'll leave that as a test for the viewer. But if the byte turns out to be 0, it goes to red 3. Well, we're in the neighborhood. Where's red 3? And here it calls another byte to get the entry point, which is the most significant byte. Then it calls another one to get the least significant byte. It checks to see if that was a 0 or not. And if it is 0, it must have or A with H. Yes. A is the least is the low half of H at this time, ORed with the high half. This is a common way to ask, does HL equal 0? And if it does, it would set the 0 flag, and you go back to where you were. Okay. Notice what this thing just did. It read a record type, and it read this address right here. It made its choice, and it went back to the monitor at that time, with all this crap still pasted in. So it got a 01FF. And if we look at what happened after we were done pasting, if it's still in my, oops. Now if we look back here and scroll back at what it did, you'll see I don't know what to do with a 0. I don't know what to do with a 1. What's going on with this FF jazz? Well, remember, F is a fill command. So what I did when I typed FF and I hit return is I said fill, starting at address F, and I didn't give it its second byte, which is supposed to be the character to fill with. So that is an error. That's why this is here. All right? So, again, this code really leaves a bit to be desired, but that's why the garbage is at the end of all the other garbage. Let's look and see why the rest of the garbage is there. Okay, this one really threw me. This is why I actually had to pour into the source code here. All right, so remember, okay, so we're not at the EOF record, so we fall through. What do we do? Also, we assume it's a data record. Okay, get the load address high byte and then the load address low byte. So those are the next 2 bytes in the record. So you can see over here, there's this 1000. Now I'm questioning myself. What's it doing? It's reading the colon. It reads the record length first. So this first thingy in here is a length. Yeah, that makes sense because this is 16 bytes worth of data. And that's 11. Okay. So there's the length. Then what is it doing here? It's going to go down here because we're not an EOF because that has a 0 for the length. We then read in the 2 bytes. There you go. There's the address, and that makes sense. Okay. And then we add on any bias if there was one in the command, and I did not give it one, so the bias is 0. And then we say what? Skip over the record type. It throws this one away. Then get a byte, put it into memory, and okay, here we go. So the first byte is right there. This is the data that's in the record that we would recognize, and here's the data from in the record from the rest of the code are all in these lines right here. So let's look at the genius that comes next. Okay, so it's reading all this junk in here. It gets a data byte. In the byte routine, like I said, what it's going to do is it's going to read 2 characters, convert it from printable hex to binary, and return it back in the accumulator. Okay, what does he do? He puts it into memory at the address in the HL register, which it must have loaded up here when it read in right here. When he read in the stuff here about the so-called load address, he puts it in BC, and wow. Suddenly it miraculously gets into HL. What am I seeing here? Oh, it's the bias is in HL. The address is in BC. So we add 0 to HL. In 8080, it's this. And now HL points to where to put it. Ooh, okay, following along. We're all in sync now, I hope. We put A into memory. Okay, then we complement A. That's the one's complement of A. So everything that was a 0 is a 1. Everything that was a 1 is now a 0. Then, he then XORs the current accumulator value with the value in memory. What does that do? If you take some value, you complement it, and then you exclusive OR those two values, what do you get? What you're getting is X XORed with X bar, which is always 1. In stark contrast to this Mensa member's comment over here, no, that is not going to be 0. If you did not do this, then this would be true here. If you store A in memory and then you exclusive OR that memory value with A, it'd be fine. That would be 0. Yes, anything XORed with itself would be 0. So then you come down here and you say call if it is not 0, which would be the case without that thing. But with it 100% of the time, every bit will be a 1. So that's why every single time this comes back and says, write an error message with all the bits that are in error as to 1, they're all 1. So this is just wrong. 100% wrong 100% of the time. You then add 1 to the so-called memory pointer, which is really the thing that's holding the bias value. You decrement E, which somewhere must have the number of bytes from the record in it, and you go to red 2, and you go around and around and around and around and around. Okay. Then what do? You get the checksum. You immediately throw it away. Call byte. Abort if error. Jump if non-zero. Wow. Well, we might have to look at byte and see what it does in there. But whatever. It doesn't do this. Go to the next record, red 0, and we back up here, and we throw away everything until we get a colon and go on our next run. So the problem now is that every single byte will show up with an error message here. I'll leave it as a test to the viewer to burn me if something really creative is happening in these bit routine or the byte. It's not, because it gets reused all over the place. These are going to do what I believe is the obvious thing. So the problem here is somebody decided to invert everything and cause it all to be wrong. Okay. Now, I did a little Googling around the internet to see if there was maybe a new version of the ROM, but I don't really want to burn a ROM, and I don't have one, and blah, blah, blah. So we're going to live with it the way it is. Very interesting. I'm going to guess no one has ever used this. All righty, let's move on to example program number 2. What do we have here? We have a tool that works as long as we know what rake left out in the yard not to step on. Okay, we understand that it's going to, at the end of every time we download something, gripe in this manner. We know that every byte's going to come back with an error. Therefore, we know we have to waste as much time as needed to print all this crap along with a carriage return and a line feed and 2 nulls with a high order bit set in it at the end of every one of these error messages. For each byte that we write out in our file. Unfortunately, Minicom will do us some favors. Probe2.hex. It lets us add the delay that you saw me do, but it puts a delay in after every single one of these characters. And, I mean, it's certainly better than nothing. Otherwise, we'd have a lot of trouble, right? At least we have it when we need it, which was after every byte in this range of the data records, every pair of characters, I should say, in this range of the records, because that's when it prints all those error messages out. And we have to waste enough time so that it can do its job before we start ramming more, data down its throat. All right, so empirical evidence is that 38400 baud with 20 milliseconds is enough for it to print that mess. Apparently. I'll have to actually do the math, or somebody can do that and post in the comments below what is the optimum value that I could use for that and get away with it. So let's go ahead and paste this whole thing in now at once and see what happens. Let's do our fill game again, 1000 to 1100 with, let's go with 80 this time. D1. Oops, that's not what I wanted to do. Okay, a whole bunch of 80s, and I'm going to go ahead and I'm going to read that, and I'm going to paste it in. It's going to complain about everything. I wish I could fix it, but it's got an OTP ROM on the board, which means it doesn't have a window. I can't erase it and reuse the chip. So I have to have another 2K EEPROM. I probably got one somewhere. Such a pain in the butt. My EEPROM programmer only works on PCs running at 11 megahertz. No. All right. We're going to live with it. What do we got? I got a con in and a con out as per the documentation, and I can call them, and I can print stuff from the C register. So what am I going to do? I'm going to read con in. I'm going to add 1 to that value. I'm going to put it in the C, and I'm going to call con out. I'm going to give myself a nice, easy target. Now, obviously, you could put a breakpoint on this instruction, but I don't want to look up in the manual whether or not I have to put a breakpoint here or the breakpoint on the one before it. It's easier to just throw extra crap in there and put a breakpoint right there. I'm sure it'll do it in lieu of, because I think the way it does the breakpoint is it replaces the opcode of the instruction that you choose to put the breakpoint with the restart instruction opcode, which means it'll die before, or breakpoint before it executes the instruction that you list, okay? But, old habits die hard. Always put a big target in there. Broadside of a barn, no confusion. Okay, so what does it do? You saw this years ago with one of my early tests on the Z80 Retro, where I read a byte in, add 1, and print it back out. Because it's the easy way to exercise your UART and know what's working. So if I say go to 1000, and I stop at, we need to look at the listing here. That's when we have a listing. I'm going to stop at 1008. Rink. Stop there. What this is going to do now is one iteration. It's going to read a character from the keyboard, add 1, print it back out. I'm going to press a capital A. And it comes back with a B, hits the breakpoint, and stops the program. So we just executed ding, 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 and stopped right there. Okay, now if we type, I think it's X, it'll dump out all the registers in this nice little debugger. I mean, they do all this work, and they actually got a debugger that seems to function okay. Program counters here and there. I mean, all this stuff works, and they can't even get a simple byte comparison checked. We all have made mistakes. I get it, myself times a million, but I can't help but think that there's no way they ever tested this code. In a commercial product, people try to suck less than you do when no one's looking. That's all I'm asking. Now, if I type G1000 and no breakpoint, it'll run forever. A, B, C, D, E, F, G. That definitely is working. The interesting thing now is if I hit carriage return, it doesn't work because it's not sending the OD. Well, I am sending it an OD, but it won't print it back. So what is a carriage return? Is a control J. So since it's adding 1 before it sends it back, I need to send a K. Was H-I-J-I. I have to send it control I in order for it to go. Actually, that's a new line to go down here. And then a control M is the other one. And if I hit control L, it would do then the beginning of line. So that's how you can get this. If you decide to run this program yourself and have trouble with it, that's the keys you want to use. Now, if I hit a 1, I should get a 2, and so on, because these are in ASCII right next to each other. 9 is a colon, 0 would give me a 1. There you go. How do I get a 0? I don't remember what comes before 0. Something like a bang or something. No. Oh, no. I can't remember what comes before 30. It's a 2F. What's a 2F? In Ascaruni. Oh, it's a slash. There we go. All right. So this is actually quite cool. It really is. In spite of all the stupid problems that I've run into with this, we now have a way to assemble programs, type them in conveniently, and upload them into the CalComp system and execute them using the monitor they gave us, in spite of its warts and bruises, which arguably are tolerable. The only real downside of all this spew in here is that we don't really have any way to check for errors, because it'll be find the missing one. You know, when it's a 10-byte program, fine. But if I upload a K like this, it'll take forever, which is unfortunate. And if there's any bad bytes, we won't notice because it'll be a noise fest. Byte errors are probably not going to be too plentiful, because the errors that they're checking here are the errors where the memory in the in the S100 bus is in error or has failed in some way. So we can kind of do memory tests for that on our own. If I reset the box, hit enter a bunch of times, there's a T command. Let's say I want to test from 100 to, I can't go all the way to the end, because remember, it uses some of the memory and you don't want to clobber it. Let's have a look-see at where that is, just for yucks. And remember, the boot ROM is in memory somewhere as well, which is at F000. So if we take a look at, I happen to know where the thing ends. It ends at BE00, and we go up to C, 100. If we look at this, what happens is, this is the end of the RAM. This is non-existent. And we'll talk more about this in another video, but the short of it is, it has a bank select system, not entirely unlike the one in the Z80 Retro. I mean, I got the idea from somewhere. That mine works very differently than theirs, however. And the point is that the upper 16K is not RAM right now in this system. It can turn it on and off and bring in other things like boot ROMs and stuff into there, and then switch it back to memory all on demand while the system runs. The junk right here is the 50, 80 bytes that they said that they use by the ROM monitor. So if I'm going to test memory, or I'm going to fill it with garbage test data, do not go beyond this point, or you'll clobber your monitor stuff. And the monitor also uses stuff around 0, under 100, the restart vectors and stuff down there. So if I want to do a fill, I can do fill, capital F, 100 to, let's say B7F, jeez, uppercase is just killing me. I can't believe that they don't have a simple translate to upper routine. Yes, they're trying to save data save memory space and all that. But I happen to know if you dump out their ROM image, there's a section that's not used. So they have bytes they could have wasted on it. What do I want? A B7FF. It would help if I could type. Fine, let's not go that far. Fill 100 to B000 with, let's say 5A. Those are a bunch of intermittent ones and zeros. Oop, D1. Jeez, this is just as nuts. 100. It's hard to do this while talking. I mean, most of it's me. But man, it would be nice if they supported a backspace. But again, adding more things makes it more difficult. And I'm sure they never used it for hardly anything at all other than dumping out memory, perhaps while debugging a system. No one has probably sat here and actually interacted with and written programs and uploaded. Well, they probably have, but more than, I don't know how many. Raise your hands. Because obviously, no one that works at this company tested or used and exercised the wonderful splendor that is this read loop here, specifically this complement instruction that takes place in there. So, I'm not going to fix this. I'm going to leave it the way it is. We're going to use it as it is. So, what was I doing? I wanted to run a test command, 100, also to B000. This will not only have filled it with memory like this, but it's going to do it and read it back and compare the two values and say, hey, okay, that memory's all good. And I happen to notice that it doesn't leave it broken, which is a nice thing. If you do this, it leaves it the way it found it. Oops, I just did it again. D100, 1000. So it puts it back the way it was. So in theory, I don't know where the stack is when this thing runs, but if the stack is down in low memory, actually it's probably in high memory. If we don't run this across the stack while it's in use, it's probably okay. Oops, DC0, wow. C100. So this is a memory hole, nothing's responding there. DEFOO to F100. This will be the transition from nothing to where the boot ROM is. Because remember we set the jumpers to jump to F000 on a hard boot, and there's a C3, that's a branch to whatever. So these are those we were just looking at the source code of this. Those are the branches in their little their vector table at the beginning of their boot code. So it's a 2K ROM. Therefore, it ends at F800. So we go to F700 to FA00. We should watch the end of the ROM as it transitions to nothing's here. Now, you can see a little bit of crud up here, and then you got all FFs right there. So I submit the ROM has all FFs in it right here. This is unused data, which is why I said you probably could have written an uppercase routine. You probably could have sucked less with the parity bits and shut them off. And you could probably also remove that XOR instruction and had plenty of room to do so. So please go back in time, somebody, and fix all that. And we will have saved some time. So F800, we're back to there's nothing there. Because the ROM only is 2K. All right? So if you ran the test routine, is my point, at C000 to just about anything, C100, that's ROM. That's all failure, okay? And it's going to give you the same failure return as it does when you're trying to upload and say all these bits came back unable to be changed from what they are, which does make sense, right? I mean, if they're immutable, these are all immutable. When it does its test, it must write all ones and all zeros and have to succeed at both cases before it says it's okay, because otherwise one of the two test cases would always work, even if it was an EEPROM, because you'd be writing a bit value that's equal to the one on the ROM. So we have the source. I'll leave that as a test. Viewer, to see how the test routine works. But what are we left with, right? What we're left with is a system that actually we can make sense of, and we can compensate for, and we can write assembly language programs like you saw me do in here, and we can compile them with the tools that we already have, even though they are not without their charms. And we can run little test apps like this and try them out on this system, and they work. It's amazing. I got to tell you, I was testing some data backups that I had made some years ago. Almost every one of them failed. And they're on old hard drive, like laptop hard drives, the little ones. All of them are failing miserably. And this thing comes right online. We'll have to try reading some old floppies next time. That'll be an eye-opener. What works better? What lasts longer? A modern-day laptop hard drive or a floppy disk from Steve Case from the early 90s? I don't know. Tune in next time for the answer to those questions and more. Thanks for watching. See you on the internet.